Hi, today we're going to continue talking about our metal ion titration using EDTA. We're going to pick up right where we left off, and that is with this image. And so the question from before is, why is it that when we have the same titration, but with different metals, we're actually measuring the same log of free metal ion concentration when we know that the metals interact with EDTA slightly differently? But the answer to that is pretty straightforward. Remember that for our region 1, our assumption is that whether or not it's strontium or calcium, the reaction with EDTA has such a positive K value that we're going to basically consider it a one-way process. And so in approaching some sort of an ice table, we're not going to have any, oops. We're not going to have any equilibrium established so much. And so if we're going to build something like an ice table, it's really going to be more of an ICF table. So at 5 milliliters of EDTA, considering that the EDTA has the same concentration, if you're adding an equal number of moles of EDTA to an equal number of moles of metal, we're going to create an equal number of moles of complex, and the amount of remaining free metal will also be equal, and therefore the PM values should be the same. It's really just because this would happen with, say, if you were saying an HCl versus an HNO3 titration, if you were just titrating both with the same concentration of sodium hydroxide and the acids had equal concentration, you would expect to see that the first region would look exactly the same. In the case of the strong base titration, you'd probably expect the whole titration to look the same. Here it doesn't, and that's kind of what we're going to get into today. So to actually figure out how the rest of this curve looks, we should probably talk about regions 2 and 3. So in region 2, we've reached our equivalence point, and all that means is that the amount of moles of EDTA we added is equal to the amount of moles of metal that we had present at the beginning of the titration. Obviously, some dilution has occurred, but then also to calculate the PM, you need an M, and the M here is in reference to the free metal. So the real question is, what is the calcium ion concentration? Well, we know that we have 100% bound metal at this concentration. But we also know that this bound metal, even though the reaction of the metal with EDTA is considered one way, once it's done, it's not done. And in that case, we're still partial to that equilibrium. Keep in mind that that equilibrium reaction looks like this. But then you also have to keep in mind a lot of things, right? So this is the equilibrium that we're going to look at. But this isn't actually the equilibrium we're going to use to solve anything, because this equilibrium would then be prone to several equilibria with several forms of EDTA, and there'd be all sorts of hectic mess going on. So here's what we're going to do. We're going to not look at it that way, and we're instead going to say we're starting with bound metal, and it's going to be involved in an equilibrium. But we're kind of starting with no reactants and all products. So you may have seen one of these before. This kind of feels a little bit like you're treating a weak acid titration a little bit. It's similar to that, and that idea of like once you're done with the equilibrium, it goes back a little bit. So after the equilibrium is reestablished, the amount of free EDTA and the amount of free metal is still going to be equal. So looking back at this equation, we need to do some work. So for our initial concentration, the first thing we need to remember is that dilution has in fact occurred. And actually, I'm getting ahead of myself. I always give you guys the opportunity. Go ahead and pause the video if you think you can solve it from here. I'll give you a little time. I'm going to stay hydrated. All right, welcome back. I'm going to pick right up with this. So to figure out the amount of bound equilibrium, metal. Wow. To calculate the amount of initial bound metal, there we go. Interestingly, you can kind of use either bit of information. You can either say that the calcium ion has been diluted, or you can say the EDTA has been diluted. Because they combine in a 1-to-1 ratio, you'll get the same number. I'll show you both. The calcium ion, so our initial is 0.0400 molar. Our initial volume is 50, and our current volume is 75. And so that would be 0.0267 molar, I believe. Yeah. Alternatively, we could have said we're going to dilute down the EDTA. That would be this. It'd be 25 over 75. And notice that the concentration is doubled, but the volume is halved, so you still get the same number. And that would be 0.0267 molar. Obviously, you're going to get a minus X, and we get a plus X, and we get a plus X. And lo and behold, we're actually going to see the same exact math we did before, where K prime F is going to be equal to F minus, oh wow, I'm going to clean that up, F minus X over X squared. Keep in mind here, let's see, as a reminder, this is 1.34 times 10 to the 10th. That is, of course, the conditional formation constant. We're at a pH of 10, so that's 0.3 for alpha. I believe it was 10 to the 8.65 or something. I wrote that down. It's somewhere. 10.65, 10 to the 10.65, that's what it was. Now going through all of this, we're going to get X, which is equal to the calcium ion concentration, is equal to 1.4 times 10 to the minus 6 molar. And then your PCA value for this is going to then be 5.85. Now, this is obviously A, not 7, and B, you would consider it acidic if we were talking pH, but we're not, and that's the important thing to remember. You might be able to draw a little bit of analogs here, keeping in mind that these EDTA titrations are based on K prime F, where the acid-base titrations are based on KW. We've taken our K prime F, and it's a little lower than KW, well, higher. It's a 10 to the 10th instead of a 10 to the 14th type thing, and that might be where part of this comes from. But as long as you got the same answer as me, I'm happy. Finally, taking a look at region 3, this is when we've added more EDTA. Now, I know what you might be thinking, oh, well, yeah, well, you just take the negative log of the excess, except here's the hard part. What is now in excess is EDTA. So what we do have is we have a situation where the calcium is in equilibrium with the EDTA and then the bound calcium. Interesting. And if we were at equilibrium, for region 2, the amount of calcium equals the amount of EDTA. If we were to add more EDTA, you would shift right. That's just Le Chatelier's principle. What you can then say is, so like what ends up happening is that initial amount you add is going to shift the equilibrium right. But what you can do is, what we should be doing is you should be calculating the amount of moles of excess. You set up an ice table because the equilibrium will bounce back. It always bounces back, right? So if you added 0.1 moles of the EDTA over the equivalence, you would say, oh, well, it won't be 0.1 moles after everything bounces out, because that would shift, like that would be a stress, but then keep in mind it always like it balances out, right? The shift right would then decrease the amount of EDTA. For the sake of argument here, there's a couple things I want to say. Actually, there's one thing I want to say. Don't do that. Just don't. Don't do that to yourself. Don't give yourself a headache. Because the value of the equilibrium constant is so large, we can again say that the shift back, any leftward shift, is going to be so negligible compared to the amount of EDTA, and we can check that when we're done. But what we have to do now is at this new concentration, we need a concentration, or at this new amount, we need a concentration of the bound metal, and we need a concentration of the EDTA. And in both cases, we're going to look at both of these as basically a dilution. The idea is that the amount, since we're going to ignore a lot of equilibrium shift, the amount of bound metal is going to be equal to whatever it was before, but we're just adding more liquid. The addition of more EDTA isn't really going to change the amount of bound calcium. Yeah, it is going to change it a little bit, but keep in mind, we were already at micromolar concentrations of calcium. So you're not really going to chew up a lot more of the calcium and then increase the amount of bound calcium by so much when if the free calcium is in the micromolar and then the bound calcium is in 27 millimolar, you're already like at 1,000-fold difference. And that's what I mean when I say we're not really going to worry about shift, like the establishment of equilibrium. We're just going to shift it in a one-way fashion. In other words, now I'm going to use the calcium ion concentration just to streamline the process and not confuse myself too much. So the initial calcium ion concentration is 0.04 molar. Our initial volume is 50 milliliters. And if we're going to do, I'm going to do the 26. I'll let you go through and do the 30 on your own. This would be a total of now 76 milliliters, which should give us 0.0, I wrote this down, 263 molar. So again, this is what I'm saying, right? Like, so if we're shifting the calcium ion in the range of micromolar, we're still in the hundreds of micromolar at our last significant digit. So that's not going to be a meaningful impact. For the EDTA, we're going to use our initial concentration of EDTA. Now we're worried about the amount of excess that's getting diluted. We treat that excess being diluted, and so we're using 1 over 76, and that gives us 0.00105 molar. And again, though, to figure out the amount of calcium that's present with these concentrations, we would set up an ice table. We're not going to set up an ice table. We're going to assume that I and E are equal, just to make our lives a little less chaotic. K prime F here is going to be equal to the complex over calcium times EDTA. Now they're not equal though. So this is 1.34 times 10 to the 10th, and that's going to be equal to 0.0263 over x times 0.00105. The hardest part of the algebra, and it's just algebra because there's no squared x, the hardest part is remembering that there's probably a reciprocal step at some point. You got to do one flip somewhere, but going through and solving that, we're going to get an x value of 1.9 times 10 to the negative 9th molar, and that'll give you a PCA of 8.73. So a couple things I can see. One, we have definitely seen there's a shift of 3 P units by going 1 milliliter over the equivalence point. So that's where I'm saying like any shift back to the left is going to be minimal because of the high value of K. But there is still a heavy shift towards chewing up a lot of that calcium. Even so, though, we've now gone from millimolar to micromolar to nanomolar concentrations. So that change in that you're going to shift back is not going to be creating a ton of free calcium. And so you're not going to be changing your other two values by a large amount anyway. So you don't have to really worry about that shift back. If you want to go ahead and calculate it, you can, but keep in mind that that x value is going to be on the order of magnitude there, and so like 0.0263 minus 0.00000002 is going to be basically the same number anyway. To let you get a chance to practice this, there's a 30 milliliters there, so I want you to go through this, everything you see there, except for 30 milliliters, I'm going to write out at least the concentrations for us to solve plug in, but I want you to go ahead and solve it on your own. Take the time that I'm taking to write it. If you need to pause, pause. If you want to start working now, and if you finish by the time I finish, all the better. Great. So hopefully you paused and you got a chance to actually complete this on your own. If we are at 30 milliliters of EDTA added, our excess here is 5. So it's all the same stuff except it's 50 over 80 and 5 over 80. So what we end up with is our bound ion concentration should be 0.025 molar. Our free EDTA concentration should be 0.005 molar. I'm clipping significant digits here to save space. Those actually end up being exact values. There should be some extra tailing zeros there. Going through the math and plugging in K prime F, you get 3.7 times 10 to the negative 10th molar, and that'll be a PCA value of 9.43. So we're not quite seeing, like, in a 1 milliliter we got 3 units of shift. In an additional 4 milliliters we got not quite 1 more unit. So we definitely have this leveling effect happening in region 3. Interestingly, we're not going to see, it's not going to approach any certain value as far as I know, because the PCA is not directly dependent upon the excess EDTA concentration, right? You're not taking negative log of 0.08 and using that as like your idea of what a maximum is, which is what we did in the acid-base titrations. So to kind of sum things up, region 1 was like a strong acid, strong base titration. Region 2 was like a weak acid titration, and region 3 is kind of unlike anything else. It's its own thing, which is kind of neat because it's like a nice review and then a nice extension. To really wrap things up, we've got 2 more things to look at. This was the second half of the, I looked at this picture in the textbook and 2 questions came to mind immediately. This is the second half. So looking at the region 3 PMs, or even the region 2 if you wanted, why is it that you're seeing lower values for strontium than for calcium? And all the information's there. I'll give you 30 seconds or so if you want to pause and think about it. I'm not going to make a comment below, but I'll just go through this, and then there's one more picture to show. Excellent. So we can see here it's these K prime F values. So the K prime F for strontium is definitely smaller than the K prime F for calcium. This means at and after VE, the free amount of calcium is always going to be less than the free amount of strontium. This is, of course, bearing in mind the idea that our initial concentrations of calcium and strontium are equal, our pHs are equal, and our initial concentrations of EDTA are equal. If that's not all true, then a lot of this goes back to we have to actually do some calculations. But the idea is if the K prime F is larger, there will be more bound calcium, all else being equal. This means that the PCA would be larger because you know that the concentration and the P are inversely proportional. It's just as simple as that. It binds more tightly in terms of equilibrium, so there's less of it floating around. That works at the equivalence point and at the post-equivalence point. So really, that's what I was kind of getting at, that the shape of your curve is actually more dependent on the K prime F, and that's what I'm getting at. If you were to consider Kw, right, flip Kw to turn it into a binding constant, you get 1 times 10 to the positive 14th. And so you can kind of imagine in like a strong acid, strong base scenario that you would see this line, oh, I can't draw a vertical line today, that would go even higher. And that's why we see numbers for post region 3 strong acid, strong base titration that are up near 12, 13, 14, but not here. Obviously you can pick other metals and you can get different things showing up in terms of binding. In fact, if you're metal binds poorly to EDTA, what you might end up seeing is, like, in the extreme case, not much of a response at all, and that would just be because the EDTA doesn't bind the metal, so we can't see a jump, and really you're just seeing the effect of dilution. And then finally, speaking of curves that don't do very much, I found a picture in the book, and then I found a picture from the internet, and both of them kind of relate to the same thing, so I was hoping everyone could take a minute and try and explain these, what you're seeing. So go ahead and hit pause if you like, otherwise I'm going to jump into it, try and trim down the length of this video a little bit. Great. So what we can see here is that as the pH is lower, the jump is different. It's shallower, less of a jump. And then as the pH is higher, the jump is more stark. On the left, we have a potential reading instead of like a PCA or a PM or a pH. We're not really getting too much into redox titrations, particularly in terms of voltage-based redox titrations at this moment. That's coming later, because we have another little bit of time left. But the idea is, it says as the pH is lower, the endpoint becomes less distinct. Why is that? As the pH is lower, the endpoint is definitely less distinct. Why is that? Keep in mind that all of these curves are based off of K prime F, which is equal to alpha Y Bohr minus times KF. As pH decreases, alpha decreases like a lot. Sometimes you can probably pick certain examples where at low pH, I need an eraser. I wish the eraser button was easier than that. It's probably like a button I can click on this. I should experiment with it. Humor me. Nope, that's right click. Nope, that's something. Okay. Neither one of those were what I wanted. Can I flip it upside down? Nope, that doesn't work. All right. Well, that was a fun experiment. At low pH, you could even imagine some situations where where K starts to approach a value of 1, or even K might be less than 1. And remember that if K is less than 1, then that's a reactant-favored process, and you're not going to see any binding, really. So at low pHs, we know that the Y4 minus form is lower, EDTA is overall less effective, and so the less effective EDTA is, the less of a jump you're going to see, because the EDTA has exhausted your metal ion, where instead you're just going to see this slow effect due to dilution, and that's about it. Thanks for watching.